все хорошо, да? Там? Ага. Okay, let's start. So first, I would like to. So we're looking at examples of super Lie groups, and I would like to remind about GLMN. So GLMN, because what follows will be a Lie subgroup, well, super Lie subgroup of that. Okay, as supermanifold, so this is, well, this is sub, well, it's a open submanifold inside R, well, R or C, but okay, let's take R, m square plus n square 2mn, right? And then here we have coordinates that are combined in 4 matrices, X, so these are coordinates X, I, J, where I and J are from 1 to M. Then you have Y, which is consists of coordinates Y, I, J, where I and J are from 1 to N. And also you have theta. So theta, so my I goes from 1 to M, and J from N plus 1 to M plus N. Sorry. Well, from 1 to N. And psi, it's the other way around. So psi ij. So here I from 1 to n and j from 1 to m. So I'm thinking about such matrix x, y. So these blocks are located like that. Theta, psi. Like this. And then if I have an S point, of this supermanifold, I can identify any S point with a matrix with blocks A, B, C, and D, where A, I, J's are pullbacks with respect to P of X, I, J. So B, I, J is a pullback of theta ij, right? C is a pullback of xi's, and D is a pullback of y's. And then points are multiplied as follows. So P1, P2 is the same as I multiply matrices corresponding to these points. A, B, C, D. And, well, so I have a functor, right, from S to GLMN S, and this is functor from supermanifolds to groups, and it is representable by this supermanifold. It's just by construction. All right, so now, after we recall this, let us talk about next example, which will be OSP M to N. All right, so suppose that I have supermanifold S, and then let me take GLM to N, so S. So this is a group, and it acts on the following thing. So OS of S, so global sections of S, tensor C M. Well, let me take now C, right? Because, well, I don't want to think about a signature, right? So M to N. Right. So it just GLMN. I mean this GLMN, but with C instead of R. And so the action is clear. So you have, so these are vectors consisting of with elements which are functions on S, and these are matrices, right? Which with elements which have functions on S. And so you just multiply matrix, vector by matrix, and this is the action. Now let me denote this somehow. So let me denote this guy by V M to N. Okay. And then let me consider an element phi. So fix phi. So this will be an equivalent of non-degenerate symmetric form. So it shall sit. So this should be an element of homomorphisms. It should be a homomorphism of all of S modules from the tensor square of this guy, M to N, to OS. Moreover, I would like, so it's from like prime, right? But I really would like this to be even, an element of even part of this. So this is square. And so such that phi is non-degenerate. Well, non-degeneracy is clear in this. So this is in particular just K-linear map, right? From here to here, and non-degeneracy, it's clear what it means. So it's just as a C-linear map. And supersymmetric. Meaning that, okay, it's a morphism from this to this, right? So I really would like the following. So if I precompose phi with braiding, right, on V M to N, then I get the same. So supersymmetry means this. So that is this should be satisfied. then I would like to define a group which I will call O. I don't know, it should be, I guess S should be also the same size of O, OSP, M to N. So I just want to remark that already at this point, since I require phi to be non-degenerate supersymmetric, it means like it is anti-symmetric and non-degenerate in the usual sense on the odd part. So therefore, I have to take 2n here. So that's why I have 2n. So I define this group. So this is for any S manifold to be all elements from the group GLM2NS such that they fix this form. So I will write it like this: phi of G V G W is phi of V and W for any, so for any G for any V and W from VMN, M to N. Okay? And then, well, it's definitely a group, right? Just usual group. But I really want this, so I have a functor S to, so OSP M to N. And so well, it sends S to this. So I would like to claim that this functor is representable. So ну, в том смысле, что что из функториальности мы хотим проверить. Ну, что морфизм, что, например, морфизм, значит, многообразий, да, этих, да, супермногообразий соответствует морфизму групп. Ну и причем он контравариантный должен быть, да. Да. Ну, давайте попробуем подумать, да, хорошо. Значит, S1 S1, допустим, у меня вот такой есть морфизм. Я хочу, чтобы, ну, значит, вот это надо как-то обозначить. Ну, пусть будет просто F. Да. Чтобы у меня был какой-то F от φ, который из OSPM2N в S2, да, в OSPM2N S1. Так, ну смотрим, значит, у меня OSPM2N сохраняет, ну вот такой, где φ, собственно, у меня зависит от S. Ну, то есть можно здесь тоже как-то писать S, да. Значит, ну мы хотим, значит, ну вот пусть у меня есть элемент такой, там G1 из Значит, ну, G, да, ну хорошо, G, ну, какой-то, у меня есть какой-то G, да, из GLM2N, ну, S1, это значит, что у меня есть, значит, ну, вот такой морфизм из S1 в GLM2N. Правильно? Это то же самое. Значит, теперь я беру и, соответственно, ну, ну понятно, куда мне его отправить. Да, да. Значит, берем вот из S2. Вот. А φ у меня из S1 в S2. Ну, понятно, куда отправить G. Значит, вот мой f от φ, примененный к G, это просто композиция. S1 в S2 и в, ну, в GLMN. Вот. Я хочу понять, что вот такое, значит, лежит, соответственно, вот здесь. Ну, значит, ну, значит, у меня была f φ S1, значит, у меня G сохраняла φ S1. Наверное, вы правы. Наверное, вы правы. В принципе, я могу абы как зафиксировать. И тогда у меня не должно получаться, правильно? Угу. Ну, они все... Ну, φ S1 и φ S2, значит... ну, я хочу сказать, что над C -то я могу выбрать какой-то базис. Всегда, что... Ну, я хочу воспользоваться тем, что как бы, у меня немного свободы. Я всегда как бы могу одной и той же матрицы как бы, представить. Ну, вот как вот просто в SO, например. Вот. У меня любая невыраженная симметрическая, это просто, как бы, вот просто у нее соответствующая матрица единичная. Но в разных базисах. Но здесь... ну, здесь-то мне нужен гомоморфизм групп. Ну, в смысле, точно сюда изоморфизм. То есть мне нужно подкрутить... Ну, не зависит от... Сейчас, ну... Тогда мне надо выбирать данные, да, для каждый раз для всех, ну, для любого f от φ от... Ну, сейчас, но мы можем взять на CM2N. Ну, в принципе, тоже, да, давайте четную, там все вот это повторим. А потом, что надо сказать, что... ну, все равно у меня же LM2N. Ну, она может действовать... ну, и пожалуйста, да, у меня есть как бы... Но она все равно, она не будет, вот то, что, значит, она не будет фиксировать конкретно вот это. Да, то есть она, в принципе, будет сдвигать вот эту компоненту, да? Ну да, вот просто как нам тогда записать условия вот этой фиксации? Ну да, то есть мы просто хотим сказать, что это те, которые действуют линейно, вот на такое, относительно, да? Получается, что так. Но на самом деле можно действительно можно так, а можно, ну вот как Николай предлагает, просто сказать, что пусть у меня есть фи s, который, значит, значит, он функториальный действительно. Ну да. So such that phi of s is factorial. Yes. Okay. Yes. Отлично. Значит, это важно, действительно. Okay, so now what about the representability? So let me try to formulate like what would be a supermanifold which will represent such a functor. So I claim that f is representable okay, so I will not prove completely this. So I would like to leave some work for you. So I will formulate the result, and well, it's up to you. You either result. Well, I kind of did it, so should be correct, and it coincides with those in Varadarajan book. But okay, so the task for you would be to either prove it or maybe fix a little bit such technical things. But I think should be okay. Okay. Anyway, so let me consider the supermanifold. Let me try to construct supermanifold, and also another so proof construction of supermanifold. So what I want, so the corresponding supermanifold will be, of course, denoted by OSP M to N. And well, it consists, of course, of topological space as usual and structure sheaf. So I need to give you topological space and structure sheaf. But then let me fix indeed. Let me fix indeed. Well, an element in here. Well, as Mish suggested. But also it can be thought of as an element in here. I just multiply by once in here. So anyways, so consider the following element. Let me call it Jm to n. So it's as a matrix consists of blocks. So here I want ones, and here I want so I divide this. So I divide this into 4 more blocks, and I will have 1 n identity n here and negative identity n here. So like this. And zeros everywhere else. Of course, this one is m, and this one is 2n. So I want this. So I'm thinking about this as, well, as an element in where? Well, just so far just in well. Well, it's just like in the morphisms, right, of C, M to N. And moreover, it's even, right? So like this. So anyways, I would like then to, so I already have my matrices, X, Y, theta, Xi. So let me take matrix A. It's exactly this matrix. X, theta, Xi, Y. So just, I just give a name to this matrix. X, Y, so denote. And then theta here, Xi here. Then let me consider super transpose of this. What does it mean? So super transpose of this is this matrix. So I just transpose X, just transpose Y. Then Xi and theta, they change their places and transposed. Right, so theta transposed here. But here I have to put minus sign. All right? So this is just definition. And then I can now consider the following matrix F. So which is it's a matrix again of the same size as A and J, and its corresponding elements I will denote by Fij, and this is just the following thing: A super transposed J M to N, and then A minus J M to N. So each Fij here, so this will be some matrix. Each Fij here is an element. Well, it's a coordinate, like these are coordinates on R m squared plus n squared to mn, right? So these are functions, like global functions on GLMN, right? HFIJ. So let me go back to here. So I'm defining n. So put n to be all elements. So this is really topological space should be inside R m squared plus n squared. so these are all x in here. Well, again, maybe I went from R to C, so C, right? And such that if I take f I j tilde, so these are just functions from this space. These are just functions on this space. On x is 0. So this is my definition of n. Well, just from the point of view of the just a set, it's something which is what O n here, right, and sp to n here. Actually, nothing else. Okay, this is n. Now I need to define O. So for every open thing in here, so for every open U inside R m square plus n square, again, C. We define well, I need this structure sheaf, right, should be on n, so therefore it should be, and in topology on n is subspace topology, right? So I should define sections on every set of this form. So I think the right definition should be is just O G L M to n of U quotient by the ideal left or right doesn't matter because yes, because it's super commutative. F generated by Fij's. All right. So this is how I defined. Oh well, then there is some work which I just check here. There are a lot of things to check or prove. Well, first of all, this is super manifold, right? So claim is that OSPM to n, which is n O, so it's a super manifold. And it's representing object for our functor f. And so this will be one of the problems, but it's a big problem. So I don't know. Well, what I would do, and I kind of did in my notes. So you need, to play a little bit with how, with all you know from just usual Lie group theory. You can define action of a super Lie group on a super manifold, and you need to prove. Well, maybe there are better way to do this, but I don't know. You can prove that actually a stabilizer of a point is a super manifold. And then, well, this will be like a stabilizer of a point. And which represents this functor. But, okay. So this is the answer. So, but something should be checked here. Okay. All right, so let me just wrap up with OSP and maybe discuss a little bit more examples. Well, we kind of skipped SL, so let us mention this real quick. So this is example number 4, but okay, kind of numeration goes back to the previous lecture. So SLMN. Well, I just give you groups corresponding to to S points. So it should be all elements G from GLMN of S such that the Berezinian of A is 1. Well, of G is 1. Okay, so this is the definition of this group. Well, then you need to prove all these things. That well, the first, that this is really a functor to groups, right? Well, in this case, I think should be clear, at least more clear for than for OSPN to N. Then, well, you need, is it representable? And then construction should be similar to OSP, but maybe even easier, right? So the yes, so or the corresponding, so right, yeah, I think the construction is just similar, right? So you have this matrix A, right? You have this matrix A. Well, the corresponding subspace SL MN, right? So again, this is like some topological space, right? And sheaf. So this topological space is really let me see. So so I have Berezinian, right? So and I have my matrix A, this one, right? So I can consider Berezinian of A and take tilde of it, right? This is a function. Then this is a function on Rm, well, C R or C M square plus N square, right? And X is then is all elements. Let me make more space for myself. So X should be all elements x from R m square plus n square, right, such that Berezinian of A tilde of x, well, this should be 1, right? Let me see if I can, so maybe it can be written just in terms of this diagonal blocks, but I kind of didn't think about this thoroughly. А это вот эта штука. Значит, вот это связано. То есть я беру А, считаю от нее Березинян. Это функция. Беру волну. Это функция на топологическом пространстве. Ее считаем, да. Ну, вообще да. Вообще да. Okay, and then OSL is, of course, just you take OGL at any. Well, this I just mimic the same thing as I did for OSP, right? So I have OSL at U intersect X is OGL of U quotient by well, I should write here everything which is generated by Berezinian of A minus 1. Okay. And then again, the proof should be the same as in OSP, because, well, again, you can, like, you have a morphism from GLMN to just C10, which is Berezinian. So therefore, GLMN acts on C10, and then you just, exploit the same machinery that you should develop for OSP. And then SLMN is just a fixed point of the corresponding action. Right. So you need really some kind of constant rank theorem over there, right? To see that something. So to get the coordinates, right? Local coordinates of your stabilizer. Okay, so this is a cell, and so this really corresponds to Berezinian being 1. Okay, what else can we do? Usually in Lie group theory, we can take different kinds of non-degenerate form, right? But here we already have 2 kinds in 1, but we still have some option that we didn't use. We could take this phi. Where is it? Okay, somewhere. We can take this phi in OSP to be not even but odd, right? So this is something that has no analogs in just even world. So we just take phi. So another example. This one is called periplectic superdeep group. So I just take phi, So repeat construction of OSP for phi, well, depending on S, also should be functorial, all that, but it should live inside well, all these homes, they're the same, right? What was that? From OS, well, from V M to N squared to OS. But I would like to take this odd. And still I want it to be non-degenerate. But the only option here is then, so all this should leave, so my OSP M to, so for OSP when I took 0 and supersymmetric, that would imply that the corresponding, so this should be even, right? So it should live inside GLM to NS. In this case, my P will just depend on one natural number, n, and it will leave, so periplectic is this one, periplectic superly group, and it's denoted by Pn. My Pn of S, maybe it's better to, okay, so Pn of S should live inside GLNN of S then. So this forces M equal to N, because the corresponding J in this case, well, it's like let's call it somehow like, so the corresponding matrix of a form, right? Okay, it was JM to N, right? In the case of OSP M to N. Well, now it becomes J. Let me somehow distinguish it from this one, J prime N N. And this will be now of this. So since it's odd, this should be zeros. And supersymmetry and non-degeneracy says that, okay, it should be 1n here and I think 1n here. And then you have all the same conditions on. So you just repeat all the stuff, and then you get periplectic superly group. Ну, симметричные, да. Ну, в смысле, вот здесь вот, да, минус. Ну, сейчас, нужно сформулировать. То есть я бы хотел такое, чтобы у меня было фи. Ну, то есть антисимметрично, но все равно должно как-то вписываться вот в наше категорное рассуждение с брейзингом. Вот. То есть вот здесь я бы все равно хотел, чтобы вот, видимо, выполнялось такое. Фи, вот S, C. Ну, здесь не M2N, да, было, вот теперь должно быть как бы NN здесь. Правильно? Я вот хочу, чтобы вот CVNN, VNN равнялось фи. Вроде бы вот тогда у меня получается такое. Вот, а что значит антисемит? Не очень понятно. То есть я хочу вот все связать, как бы я переставляю только вот с помощью этого все. Okay. Well, there are also Q series which doesn't. You cannot define it using just a form. There is a much less trivial. So you need, instead of Berezinian, you need a so-called like odd determinant, which I didn't learn yet what it is, but there is like odd determinant which goes not to R like K1, 0, but K0, 1. And then you use this, and then you get some analog like of SL, which will be like a Q series or queer superly group. Or queer superly algebra we'll look at, and maybe we'll see the construction of queer superly group, but I'm not ready to discuss it just now. But this one just comes kind of naturally, right? So we discussed phi for OSP. Why not take some other option? So and then we get periplexic. Yes. Also, yeah. So if you want to look at the examples written in Deligne-Morgan, like a standard reference for courses like on supersymmetry, like mathematics and supersymmetry. So Deligne-Morgan, I think, notes on supersymmetry, something like this. So Varadarajan doesn't discuss this. Well, OSP he does, but P and Q series not. Okay, let me now wrap up with examples. And next thing that I want to discuss is, well, if I'm given superly group, then what is superly algebra for superly group? So let us discuss this. So superly algebra of a super Lie group. Okay, so let me fix my super Lie group, and I will call it G. And of course, super Lie algebra will be tangent space at identity as a vector space. So G. So we consider super vector space G, which is just tangent space at identity. Well, here I'm using notation a little bit. E is a, well, it's a, well, abusing and not in the same time. So we'll see later, but E was a morphism, right, from point to G. So here I mean like an image of this morphism, if you wish. Because here should stay some point, right, of a corresponding topological space, like according to our definitions. But in a minute, or maybe 10 minutes, you'll see that actually this is not abuse of notation. We can think of tangent space at S points. All right. So, okay. So let me take two elements, x and y, from G. So take two elements, x and y. So I would like to just define a Lie bracket. And I will do this first for homogeneous elements, and then I say, okay, then extend by linearity. So x and y homogeneous. then let me denote Rx. It will be either R10 or R01, depending on the parity of x. So it will be R, of course, 10 if x is even, and otherwise R01. So if p of x is odd. And the same for, so similarly for Ry. Similar for Ry. Then let me consider, okay, fix some element phi of x. So this will be an element, it will be Rx times Ry point of G. So G of Rx times Ry. Such that, so I want, so it's a morphism from this product to G, right? So I can just, I need something from it, the pullback. So phi x star, so should be, well, if I apply it to a function on G, should be a function in here. So let me fix name somehow. Coordinate here I will name T, and coordinate here I will name S. Right? So these are corresponding coordinates. And so I would like this to be of the following sort. First f tilde of E plus, so since I have x here, I would like T times x. So x is super derivation at a point, right? So I can actually take and apply it to the stock of f at E, right? And then plus something which is so maybe mod I t squared plus is squared, so where IT is just ideal generated by T, and IS, so it's like that. And IS ideal generated by S. Okay. So I really need phi x that looks like this. Well, the existence of such thing, so maybe let me try to give you some. Well, and of course I want for x and y. So for y similarly, I just need s in here. All right. So let me just maybe try to give you one example of such phi x. Of course, you have some freedom to choose. But one option would be what am I saying? Yes, I think everything is fine here, and I didn't I save everything I want. Okay. So, for example, I can take phi x defined by default by its pullback. So I just apply. So again, this is using like a loose notation here, but it will be clear what I mean. I take f, my f, and apply exponential. So exponential of t of t x, well, maybe vx here, and then like evaluate at e. Okay, so this is like should be in quotation marks, but what? So here, so where Vx is a vector field on G, so vector field, such that if I apply it and then evaluate at identity, this will be the same as x. So this is like a composition of two things that I do with the function f. And E star just does what? It actually takes, so E star actually does the following to f. It's just a side note. It's just the following. Well, maybe tilde should be on the top of f only. Да. Ну, вот без. Ну, да, вроде бы без. Ну, а их, да, надо переносить, типа, да. Но вот это хороший вопрос, что надо, то есть я реально чего хочу? Я хочу, чтобы это был, гомоморфизм колец. Чтобы фи со звездочкой от FG это вот фи звездочка от F и звездочка от G. Вот, но я знаю, что вот это значит, производная. Вот. Но может быть, может быть, мне надо минус ставить, а может нет, надо проверить. Вот. Но конструкция, значит, понятно, что как бы при степени t там стоит вот степень vx. Вот переносить или нет, если честно, надо проверить. Вот. Кстати, хорошее упражнение. Да, но это как бы тоже вот, если у меня есть дифференцирование возложивого экспонента, будет автоморфизм алгебры. Вот. А в данном случае, вот это все равно, в смысле, это все равно будет автоморфизм, правильно? То есть мне не важно, может быть, мне даже не важно, значит, нужен минус или не нужен. То есть вот в этом члене у нас все равно вылезет вот то, что надо. То есть вот если у меня есть супер, если у меня есть супер дифференцирование, и я просто формальный экспонент от нее, то это будет, значит, морфизм, значит, гомоморфизм алгебры или нет. Или там надо какие-то минусы еще ставить, вот не знаю. Вот сейчас мы придумываем какую-то экспоненту для супергрупп. Вот. Поэтому и кавычки, да. Значит, с точностью до минус это как бы обычный, конечно, просто как пряд, я считаю, что. Вот. Ну, а вот это понятно, что значит. Это якобы вот t она игнорирует, а ну, она при t там какие-то функции стоят. И якобы их ну, pull-batch относительно единицы в g. Вот. Ну, вот, например, здесь я как бы применил vx к f, да, а потом как бы взял и со звездочкой, это вот, собственно, оно и будет. Вот. Окей. Значит, ну вот такое. So then, so similar stuff where I think I wrote it, maybe not. So similar stuff we want for y. So similarly for phi y. And then I consider a group. So these are elements phi x and phi y, they're elements of a group. So I can multiply, take inverses. So I consider group commutator. Phi x, phi y, phi x inverse, phi y inverse. So this is also in grx times ry. And then I'd like to make the following claim. So proposition: there exists unique superderivation z. Well, unique, it depends on x and y, but doesn't depend on phi. That's what I mean. So it is in T, E, G, such that, well, I take my phi, and, well, I just, well, this should be, so I take my phi, so I can pull back with respect to phi of a function on G, right? So this will be just f tilde of E, and then plus, then I have a sign depending on the parities of x and y. And then t times s, z, applied to the stock of f at E. Modulo, again, I t squared plus I s squared. This is the statement. Let me, and so the proof is just to mimic the same thing in Lie group theory, but okay, it's actually it's pretty fun to do all the technical details. And so maybe let's see. So we have 5 minutes. Okay, I think it's a good use of this 5 minutes. And so let's prove this proposition. So, proof. Okay, I take phi star of f, and I then write it as follows. So it has, it is a function in our x times ry, so I can Taylor expand it, right? Well, anyways, it has constant term, right? Which is just, let me call it, I don't know, C1. It depends on f, of course, right? Plus C2 of f, and it's a coefficient for t, plus C. So I just write general element of a function on Rx times Ry. Right? It has constant term, some coefficient for t, some coefficient for s. All these coefficients depend on f, of course. And then you have coefficient for ts. And then something that we don't care about. Okay. So then I would like to mimic the putting t equals to 0, s equals to 0. Right? So I actually have these morphisms. Let me call it LT0. So this is morphism from Rx to Rx times Ry. And I just give it by pullbacks, so of coordinates. So L star of T0 of S is 0, and L star of T0 of T is T. So this is morphism. Okay. So let me, and also I have the corresponding morphism as an image of this functor G. Right? I have this functor corresponding to super Lie group, LT0. Well, it is from G Rx times Ry to G. So this functor is contravariant, so it goes backwards. G to G Rx. So I claim that L T0 applied to phi y is just identity in G Rx. Because, okay, my phi x is, well, phi y, right? I mean, I need to put s in here, right? And y in here, right? So what does it mean that I apply this pullback? It means that, well, I just put s equals to 0. And so I put s equals to 0. So here I will so it's mod is square already, right? So and well, all this becomes 0. All this tail becomes 0, right? If I have y here and s here, right? So my phi y star becomes just evaluation at e of f tilde, which is exactly the identity in this group. Ну, S там, да, тогда ей не получится. Ну, значит, здесь вообще оно не должно зависеть от S вообще, как бы. Мод и S вообще вот как бы вот так, видимо, надо. Ну, как бы понятно, что как бы я пишу от t, но это как бы функция здесь, она, которая от s не зависит вообще. То есть вот мод и t, как я должен написать? Значит, ну, во-первых, мод и t в квадрате, да, Ну, я просто беру, я просто смотрю на эту функцию, как на функцию на g от rx, да, ее вкладываю, ну вот, ну, в смысле, как элемент g от rx, да, и ее вкладываю вот в эту группу. Ну, как функция от одной переменной вкладывается функция двух переменных. Вот. Это я хочу. Да, то есть вот давайте так видим. Ну, так или не так, не важно, но как бы doesn't depend on s. Да. Да, и тогда правильно. Ну и, соответственно, тогда же я так положил, то я могу взять теперь g, l, t, 0, ну, применить к φ большому. Да, у меня тогда получится просто φ x на φ x минус 1. Ну, а это тоже единица уже от rx. Правильно? Ну, а это значит, что на самом деле, чего я сделал? Я положил как бы здесь, здесь я положил s равняется нулю. Да, то есть я стер вот это, а вот это не стерлось. Да, и это стерлось. Ну, а должно было получиться identity. Вот. Поэтому вот это должно быть 0. C2 от T0. Ну и C1 от F это на самом деле F с волной от E. Так. Ну и so similarly I can consider G of L0S so if I do all this with L0S, it will give me that C3 should be 0, right? C3 of F is 0. So actually I have phi star of F is just F tilde of E plus something, C4 of F TS mod IT squared plus IS squared. But then I need the fact I need to use the fact that phi is star is homomorphism of rings. It means so if you, but we did this similar exercise a couple of times already. It means something that C4 up to a sign is actually superderivation. So phi star is homomorphism of rings. So this implies that, well, the signs should be recovered upon, just straightforward check, but so the result is that it should be -1 to the p of x to the p of y, which is the same as p of t, p of f, s, z applied to f of e for some z which depends, of course, on x and y, and for now on phi of x, phi of y from t e g. And now the only thing to do is that to claim that z depends on x and y but it doesn't depend on phi x and phi y. Well, this is just again because if I take different phi x and phi y, the difference will be in this ideals, right? Because for different phi x, phi y, difference will be in it squared plus is squared. Which, of course, requires just straightforward check again. Idea is clear. It's just mimicking the idea from what we know about Lie. How it's done in say, Winberg-Kanishik in usual Lie groups. Okay. So that's everything that I have time for today. So let's stop.